All right, so it's Tuesday. We're getting ready to, I reckon, coming down the home stretch. I think, if I remember right, I could be wrong on this. Next Thursday, I believe, is our last day of class. So, short time, less than 2 weeks. This semester will all be over. In fact, it may be, I think 2 weeks from today is our final exam. So, just to update you, obviously yesterday was test day, and I've graded the first two problems. Hopefully, if all goes well, I'll grade the other two problems this afternoon, this evening sometime. So might have those done and results for you tomorrow. We'll see. So what we're going to do today is continue something we started, would have been last Friday, over in chapter 11. We're talking about beam design. So basically we're going backwards from what we did in chapter 6 and 7, where we had the size of the beam, we calculated the stress. In this chapter, we're given the allowable stresses, normal stress, shear stress, and we're designing or determining the size of the beam that must be used. And just remind you, refresh your memory, on Friday, we went through and worked one example. This was I call it custom made beam. And we did that example. And then last thing we talked about was standard size beams. And there's tables in the back of your textbook that have these standard size beams. And all we talked about was basically what the designation means, how these things are identified, and what those numbers mean, the different shapes. And that's what we're going to focus on today is designing a beam by choosing one of these standard size beams. All right, so that's where we're at. And any questions before we get started? No questions. Okay. Well, what we're going to start with is something that we saw back in chapter 6. Remember, we had this formula for our maximum normal bending stress that sigma max was equal to mc over I, where this c was just the largest magnitude of y. So in other words, it's the furthest distance you can get away from the neutral axis. That's where our maximum bending stress is going to occur. And it's going to be either at the top or the bottom surface, whichever one of those is further away from the neutral axis. But now I want to define a different term that we have not seen, at least not in this class to date anyway. So we're going to define this thing, it's called the section modulus, and we're going to use capital S. And we're going to define that to be the moment of inertia divided by C. C being the same thing up here, it's Y max. And again, this is called the section modulus. Units should be pretty evident. Inertia is length to the fourth, and we're dividing by a length, so it's going to be length cubed. So it's just a ratio involving a moment of inertia and C, and this is what we're going to use to pick our beam out of that table. We'll see in a minute. I'll put a table up so you can see it. There's a column that gives the section modulus for each of those beams. So if we define S as being I over C, then our maximum bending stress then is now whatever the maximum moment is divided by the section modulus. Or how we're gonna use this is to get the required section modulus, right? To solve this for S, we take whatever the maximum bending moment is and divide by the allowable stress. So we set our maximum stress equal to the allowable, solve for S, and that tells you the required section modulus so that you don't exceed that allowable stress for whatever that maximum bending moment is. So kind of outline a step-by-step procedure here. And again, this would be the procedure we're going to follow for choosing standard size. Beam design. Now I'm going to give you kind of my version. There's also a procedure listed in your textbook if you want to read through that and see how he describes this. It might be slightly different. Maybe it makes more sense the way he presents it. I don't know. But the first step is going to be draw our shear and moment diagrams. Yeah, this is what we did back at the beginning of chapter 6. Was first problem on test yesterday was to draw a shear and moment diagram for a beam. And the purpose or reason for that is that's where we're going to get our maximum shear force and our maximum bending moment. And this is also why I think I mentioned this maybe early on the semester, how our final exam wasn't going to be comprehensive per se. It was just going to be over the material since the last test, but you're going to see a lot of stuff we're doing from here on out requires you being able to do some of the earlier stuff. So in a way, it's kind of comprehensive, right? So you got to know how to draw a shear and moment diagram. So once we get our maximum shear force and our maximum bending moment, that's where we're going to compute the required section modulus. All right, so we're going to get our required section modulus by taking whatever that maximum bending moment is. Again, we're just looking at magnitudes here, and then divide by our allowable bending stress. It's a good point to bring up our previous discussion last Friday. When we design a beam, we design it to satisfy bending, because the vast majority of the time, that's going to be the most critical stress in a beam, is the bending stress. And so that's how we choose the size of the beam, is to satisfy bending. And then once we choose that size, then we check to make sure that that size beam we chose also satisfies the allowable shear stress. If you do it the other way around, probably 90% of the time, you're going to find if you choose the beam to satisfy shear stress, it's not going to be big enough or strong enough to satisfy the bending stress. And so you're going to have to go back and start over anyway. So we start with bending. And then once we have our required section modulus, next step would be to select the lightest. Here's where becoming good engineers comes into play. We're looking for the lightest, and the reason we're choosing the lightest, besides other benefits, especially if you're aerospace, weight is so critical. You always want the lightest, but in other applications, it's not so much as big a factor. But the reason we're choosing the lightest is because it is the cheapest. I spell that right? I don't know. When you buy steel beams, basically you're paying for the steel. So the lighter the beam, the cheaper the beam. So we're going for the lightest beam from this table. This will be in Appendix B in your textbook. There's tables for English units and there's tables for beams with SI dimensions. So sure you're using the right table back there in Appendix B. So we're going to choose the lightest beam from that table that has a section modulus S that is greater than our required. You could put greater than or equal to, but the odds of you finding a beam with the section modulus exactly equal to the required is slim to none, basically. So we're going to choose one that's got a section modulus greater than what the required section modulus is. And one note here very important for you to keep in mind and remember, the beam with the section modulus closest to the required is not always the lightest. So you can't just go to that table and say, fine, I want the S as close to the required as I can get. That might not be the lightest one. And we'll go through that process here in a minute. But I'll just mention now that the beam with the section modulus S closest to the required is not always the lightest. And again, when we work through an example in just a minute, you'll see how this plays out. Because if you can get a lighter beam that has a larger section modulus, I mean, that's a win-win. You get a cheaper beam and it's stronger. Basically, S corresponds to the strength of the beam, because S is basically a moment of inertia, which basically gives you the strength of the beam. So larger the S, the stronger the beam. And then finally, the last thing, which a lot of times students forget to do, but very important, is you have to check the shear stress for this chosen beam. So whichever beam you choose, just a second. We're going to calculate what the maximum shear stress is and verify and confirm that it is indeed less than the allowable. So that's basically what we're going to do, is we're going to confirm that tau max is less than or equal to the allowable. If it is, then the beam we chose is good. And that's what's going to happen, again, 90-something% of the time. You choose the beam big enough to satisfy bending, shear stress is almost always going to come out to be okay. But I'll just mention, if you do get to this point and the maximum shear stress is larger than the allowable, then that's one of those small times that it happens. You've got to go back and get a bigger beam. Now you're going to size the beam to satisfy the maximum shear stress. Right? Now, when we go about checking the shear stress, there's a couple of possibilities here. One, In most of these problems where we're selecting standard size beams, most of the problems in the book are asking for I-beams. So you're going to see a lot of problems in this category. And in the real world, you see lots of I-beams as well. So for these wide flange I-beams, here's where we can use that approximation I told you about back when we were in chapter 7 and doing shear stress. Because we're not actually don't need to know what the actual maximum shear stress is. All we need to know is that the maximum is less than the allowable. If that's true, we're good. And so here's where you can use that approximation where tau max, again, it's approximately equal to, again, whatever the maximum shear force is, just divided by the area of the web. Right? We don't have to go through and do VQ over IT for this I-beam. And the area of the web is, that's what I'm talking about is, again, these top and the bottom horizontal pieces are the flanges. This vertical section, that's the web. So that would be the, and I mentioned this when we ran into this earlier. This basically gives you, it's a conservative approximation. So it's going to give you a shear stress that's just slightly larger than what the actual is. So if I use this and it's less than the allowable, then I know the maximum's less than allowable and we're good. Okay. So you can use that here. You know, and I told you the test you took yesterday, if I asked for find tau max, you had to use VQ over IT. You couldn't use this, but here you can, because we're just confirming that this maximum is less than allowable. Now, if you've got a rectangular cross section, and so if you've got a cross section, it's just a rectangle. Here's where you can use that formula that we saw in chapter 7 as well. It's just 3/2 V over A. Again, it saves you a little bit of time. You don't have to calculate Q. You don't have to calculate I. You just do 3/2 V over A. Now, if you've got some other cross section, that's where you would have to use tau is equal to VQ over IT. You have to go through and actually calculate what Q is, calculate what I is, and get the maximum shear stress that way. But most of these problems that are in chapter 11, a lot of like the one we did where we did the custom design, it was a rectangular cross section. Most of these standard size beam problems are going to be I-beams, and we can check it that way. But very important, you got to do this because I say the vast majority of the time you're going to find maximum shear stress is nowhere close to allowable. You're way good, but this is just a cautionary suggestion out there in the real world. If you don't do this, you get lazy. Well, guess what? That 1% of the time when the shear stress is not okay, that's going to be the time you were lazy and didn't do it, and the beam's going to break, structure's going to fall down, going to cost a ton of money, might kill somebody. So don't not do step 4 there. All right, any questions about the procedure there that we're going to follow? Two other little sort of general comments, and then we're going to go through and work a problem. I think I got room to squeeze this in on the bottom down here, this sheet. So just a couple of little notes. One, the weight of the beam is usually neglected. So the weight of the beam is usually neglected. Now, the reason for this is good sound engineering principles that if you actually, once you choose the beam, if you went, because before you choose the beam, you can't include the weight of the beam because you don't know what beam you're using. So you would have to go through all of this procedure. And once you choose that beam, go back and add the weight of the beam to the loading that's on the beam and go through all this again. And I'll be honest, it's a big waste of time. The way the beam is not going to affect which beam is chosen. The weight of the beam itself compared to the loads that are applied to the beam make a very, very, very small difference in what the actual stress is. In reality, yes, it does add just a little bit, increases the stress on the beam just a little bit. But it's not going to be a big enough difference to change your choice of beam. I'll go back to a couple of things. One, remember we're choosing an S that's greater than or equal to the required, but we're never going to get one that's exactly equal to it. So we're always going to choose a standard size beam that's a little bit bigger than was needed to begin with. And almost always that more than compensates for the weight of the beam. Another thing to keep in mind is we've got safety factors. You know, we talked about factors of safety earlier in the course. We're not going to design this beam so that it's, right at the, breaking point, so that if you added the weight of the beam, that would cause it to break. We're going to have factors of safety usually of, depending upon the application, most times at least like 1.5 times, the own yield. So adding the weight of the beam is not going to do anything. I've seen one mechanics and materials book in all the many, many mechanics and materials books I've looked at that actually does this and goes back and adds the weight. But I can tell you from personal experience in the real world, I've never seen a real engineer in the real world do this. So we're neglecting the weight of the beam. Second thing, is I told you up here, we're always going to choose the lightest because it's the cheapest. Occasionally, you will have other factors that would prevent you from choosing the lightest one. So you could have other factors could prevent choosing the lightest beam. Now, you're not going to have to run into any of these in this course. This is just, for information purposes when you get out there in the real world. Without any other constraints, you're always going to choose the lightest because it's the cheapest. But just say, for example, like one possible, other factor I'm referring to here would be you could have space or size restrictions. For example, maybe I don't know, what you're designing here, what kind of structure you're designing, but maybe this beam, it has to fit between two other, members, or it's got some other boundaries or constraints. It could be that the lightest beam is too tall or too wide. It won't fit where you have to use it. Which in that case, obviously you can't choose the lightest one if it won't fit where you want to use it. So that would be an example of what I'm talking about here, where something else could prevent you from choosing the lightest one. One of the other ones I'll mention is I think I brought this up when we started talking about bending beams. You could have local buckling, and especially if you're using wide flange I-beams. And that was one of the things I mentioned why it was important to differentiate between tension and compression when you're bending something. And this local buckling is, say we've got this this I-beam. It's got really wide flanges on it. If we bend this thing this way, this top is going to be in compression. And what you could see is this really wide, thin flange could, I don't know, ripple, look like a wave. That's what we call local buckling. And that's something that you would have to check. It could be that this lightest beam has really wide, thin flanges, and it would experience local buckling. Then you can't use that beam, right? Because you don't want your beam to do this. And there are probably a few others we could come up with, but I just want to give you a couple examples of, in the real world, these are some things that you would have to consider that might keep you from choosing the lightest. In this class, for your purposes, pick the lightest one. Okay? All right, so any questions before we go through and see if we can choose one of these, choose the best standard size beam? All right, well then let's go. Let's see. Here's our example. We're asked to select the lightest W shape. Remember that W, these beam designations, the first thing is a ladder. The W stood for wide flange I-beams. So that's what we're going to do, is choose one of these wide flanged I-beams, the W-shaped beam. That will support let's see, the loading shown. All right, so I'm going to draw a picture in a minute. We're going to have a beam with the loading on it, and we want to choose the lightest wide flange I-beam we can. We are told that whatever this material is, yield stress is 300 megapascals. The yield stress for shear is 120 megapascals. And we've got a factor of safety on yield 2.0 is required. All right. And here's what my beam looks like. Let's see, looks like it's a total of 5 meters long. And we got a nice symmetric loading on here, like 10 kilonewtons, 20 kilonewtons, 20 kilonewtons, 10 kilonewtons. And it's simply supported. We got a pin support at that end A. We got a roller. This end B. 1 meter. Between each of those. Right, so there's my beam, the loading that this beam has to support. We're told or given the material properties of that, whatever, maybe it's a steel. And we're also told what factor of safety is required. So again, this is kind of my point, and this goes back, and you got to know about factors of safety from earlier in the semester as well. But the factor of safety is going to tell me what the allowable stress is. So I know if the yield strength of this material is 300 megapascals and I got to have a factor of safety of 2, then my allowable normal stress, is the maximum normal stress this beam can see, is 300 divided by 2 is 150 megapascal. Likewise, the largest shear stress this beam can see is 120 divided by 2, which is 60. Right? So that's how we get our allowable stresses. Now, step 1 in that procedure was to draw our shear moment diagrams, figure out what Vmax and Mmax are. So we got support reactions here. Right? We got vertical reaction forces. As usual so far, AX is possible, but it's 0, so I didn't write it on there. Now, we could certainly apply our equilibrium equations and calculate those. Sum the moments about A or B, solve for the other one, then sum the forces in the Y to get the other one. But here we can take advantage of symmetry, right? If you notice, the loading is symmetric, the spacing is constant throughout. There's no need to go through. We can just, from symmetry. I know AY is going to be the same as BY, and it's just going to be what the total force is divided by 2. So I got 10, 20, 20, and 10, that's 60. So it's going to be 60 divided by 2. So each one of these is going to be 30 kilonewtons. Again, just making use of symmetry to save ourselves a little bit of work. All right. Now let's draw our shear and moment diagram. Again, this is the shear force, and it is in kilonewtons. And hopefully by now, at least grading on your tests from yesterday, most of you did a pretty good job. Some of you obviously maybe didn't practice enough. But this should be quick and simple construction here. Here at this end, it's going to be whatever that support reaction is. So we're going to start up here at 30 kilonewtons. And it's constant. It doesn't change except when the load changes. So we're going to go down 10. Put me at 20. And then we go straight across till we get to that force, and we're going to go down 20, which puts me at 0. Go straight across, it doesn't change till we get to another load change, so then we're going to go down 20. So it's going to put me at minus 20. And then we'll go straight across till we get to that force, and we're going to go down 10. Puts me at minus 30. So I know Vmax, in this case, it's the same positive, negative, or the same magnitude, but if one was bigger than the other one, that's what you want, is the largest magnitude, 30 kilonewtons. Quick, simple, easy. Shouldn't take you less than a minute to do that. At this point, I will think, when I'm thinking about it, I'll point out. Now, I specifically, told everybody for the test yesterday, this is how I wanted you to draw, shear moment diagram. I didn't want you to cut it and actually get the equations. If you do that, what took us less than a minute here now turns into a several page worth of work. You'd have to cut this 1, 2, 3, 4, 5 times. It's not necessary. We can draw the diagram without doing that. Right? Any question about our shear diagram? All right, now to construct our moment diagram, yeah, this is our moment. These are kilonewton meters will be my units here. I know from looking at my beam, right? Focus again for me. Come on. There we go. If you look at this end of the beam, there's a pin support there. There is no moment applied. So the moment at this end is going to be 0. So it's going to start here at 0. And we're going to go up or down, whatever the area is, under the shear curve. So here, this is again 1 meter. That area is 30 times 1, which is 30. And it's positive. It's above the axis. We're going to go up 30. So we're going to go from 0 to 30. Again, the shape of the curve, it's 1 degree higher. This is constant. This is linear. Then we're going to go up whatever this area is. Again, the horizontal distance is 1 meter. The height there is 20. So we're going to go up 20. We're going from 30. We go up 20. We're at 50. Constant shear diagram, linear moment diagram. Now here we have 0 area. So it doesn't go up or down. Right? It stays constant. Goes straight across. Still at 50. And that looks curved, but that's just me, can't draw a straight line. All these are linear. And now we're going to go up or down this area. Which again, it's 1 meter wide. 20 is the height, so it's negative 20. We're going down 20. So we go back down to 30. Linear, straight line. And now finally, we're going to go down this area, which better put me back to 0, because the same reason the moment was 0 at that end of the beam, the moment better be 0 at this end as well, because there's no moment there. It's a roller support. Roller can't provide a moment, and there's no applied moment. And in fact, if you look at the area, it's 30 times 1 is negative 30. We're going down 30, puts me back at 0. Now again, if you look at these values, they're all positive, but if we had positive and negative, choose the largest magnitude. In this case, 50 kilonewton meters. So again, this is a skill that you can't analyze beams if you can't draw a shear moment diagram. It's not hard, not difficult. If you see, took this really no calculations at all, other than multiplying 30 times 1 and 20 times 1. Simple math. But any question about our shear moment diagram? All right, so that brings me to the next step in our procedure, and that was to find what the required section modulus is. Remember, we're going to choose the beam based on bending. So this required section modulus was whatever our maximum moment was divided by the allowable normal stress. So our maximum moment was 50. Those are kilonewton meters. So I'm going to go times 10 to the third to get newton meters. Our allowable 150 megapascals. 150 is megapascals, sorry, is 10 to the 6. So these are Newton meters. Pascal is newtons per meter squared, so all my units are compatible. And so this comes out to be 333.33. We'll just stop there. Times 10 to the negative 6. These are meters cubed. Now, I'm going to convert this into millimeters cubed because you're going to see in just a minute, I know this ahead of time. The table for S is in 10 to the negative 6, or 10 to the third, millimeters cubed. And that would be 333.33 times 10 to the third millimeters cubed. And again, the reason I'm doing that is because that's the way it's going to be in that table. All right, so this is our required section modulus. That's what we're going to go to that table and choose the best beam. Any questions how we got the required section modulus? All right, so I made copies of, obviously we're dealing with SI units here. So if you go in the back of your book, it's on page 810, it's Appendix B. This is for, obviously, if you look at this, SI units. And where the table starts, you'll notice it starts with the bigger beams, and they get smaller as you go down the page. Right? This is the biggest beam that they have in this table, and there are much more extensive tables out there. This is just a good sampling. But it starts out with, this W610 by 155. That's 155 kilograms per meter. That's a bunch of mass. But you notice they're getting smaller as you go down the page. And then when you continue over to the next page, it continues. The bigger ones are a little bit smaller than the bottom of the last page, but they're getting smaller as you go down. At the bottom, these are the smallest beams. And so remember, we're looking for the lightest one. So the best way to go about doing this is to start with the small beam and work your way up, as opposed to start with the really big beams and go down. We're trying to find the smallest one. Now I'm going to write up here what our required section modulus was 333.33 times 10 to the third millimeters cubed. Right, that was our required section modulus. So what we do is come down here again. I start at the bottom with the smallest beam possible. Now we're coming over here to this column. Right, this is again in this table. What they're labeling the XX axis, right? That's what we called our Z axis, our neutral axis. So that's the section modulus, the axis we want to use. That's the axis we're bending this thing about. Okay, so that's why we're looking at the XX axis. And notice it is 10 to the third millimeters cubed. That's why I converted in that. So we go to the bottom. We're looking for something in this column that's at least 333.33. And so if we look at these W150s, starts out at 91.2, goes up to 274. None of those are big enough, right? They're not strong enough. So we got to go up to the next bigger size. This is next group, W200s. And we go up till we find one, right? That's bigger than 333. Right, so I've got this, come up here and write, that's a W 200 by 36, right, and its S is 342, and that's all understood. It's 10 to the third, but we're looking at those numbers. So that one would work, right? It's strong enough. And this is the other number we got to pay attention to, is 36. That's kilograms per meter. We want the lightest one, right? So now if you notice in the W200s, everything above that is strong enough, but it's also heavier, right? So that's the lightest W200 that would work. So now let's go up to the next group. Go to the W250s. Find one there, starting out 179, 307. That's the first one I come to that's bigger than 333. But it's a W250 545. Right, and its S is 535. So that's way strong enough, way more than we need. But between those two, the W200 by 36 would be a better choice because it's lighter, it's cheaper. This one's heavier, so we definitely don't want that one. But let's continue, and maybe we can find one better than the W200 by 36. So everything above that is, you can see, it just gets heavier. So go up to the next group. We start at 244, and then we come up to this one, 415. That's the first one that is bigger than 333. So it's a W310 by 33. And its S is 415. Right, so we already decided that one's out, right, because it's 45 kilograms. But now let's look between these two. Which ones would be the better choice? Well, this one is lighter, right? It's only 33 kilograms per meter. So it would be a better choice than the W200 by 36. You notice we get the added advantage. It's stronger too, right? Its section modulus is 415. That's better than 342. So here's an example of where I mentioned earlier, the S that's closest to what's required is not always going to be the lightest. Right? We can get a stronger beam that weighs less. It means it costs less. So between the first one and that one, this would be the better choice. But don't stop there. Let's go to the next, the previous page where the beams are getting bigger. Right? And again, we're looking at this, the W360s. Well, the very first one is bigger than 333, and it's a W360 by 33. So I'm going to write that, come back over here, a W360 by 33. And its S was 475. Right? So that was this beam at the very bottom down here. W360 by 33. Now, if you look, everything above that, there's nothing less than 33. So every beam above this weighs more than that one. So none of those would be our choice. So now let's come back and decide which one of these two would be the best choice. Because again, we pretty much we eliminated this one because it's 36. So we got two candidates, but they both weigh the same. So they're going to cost us the same amount of money. So which one do we choose? If they both weigh the same, anybody want to offer a?
Choose the one with S equals 475.
Right. That's the best choice. They weigh the same. This one's stronger. So why would you not want a stronger beam for the same amount of money? Right? So that's why we want to choose this W360 by 33. Right? So I know we're basically out of time, but we don't have but one thing left to do, and that's to check the shear stress. So give me about 2 minutes, we'll finish this up. All right, so we chose the W360 by 33. Again, that was the lightest one and the strongest one. 475 times 10 to the third millimeters cubed. So it was the same weight, but it was stronger than the other one. So what I want to do now is we need to check what tau max is for this W360 by 33. That's the one we chose. Let's make sure that beam, we don't exceed our allowable shear stress. Now, here's where we're going to use that approximation. So for this W360 by 33, I need to go back and look and get some dimensions. So if you go back and look, the depth, that's the total height. That's, we'll do that. So the depth is 300, off the page, 349, these are millimeters. We need the thickness of the web. It's 5.84 millimeters. And to get the area of the web, we got to subtract off those two flanges. Right? So we got thickness of the flange here and here. It's 8.5. Right, so now I'm going to go back to my picture over here. I'm going to add those numbers in. This was D here was 349 millimeters. The thickness of the flange, 8.5 millimeters. The thickness of the web, 5.84. Right, so we want to calculate the area here of the web. We just take that depth minus two of those flanges and then multiply by the thickness of the web. That's how we get that rectangular area. So we take the depth, subtract off the two flanges, that's the height of the web, multiply by the thickness. So we're using tau max. Here is V max over the area of the web. So V max was 30 kilonewtons. 30, I'm going to put everything in newtons and meters, so that'd be 30,000 newtons. So the depth was 0.349. These are meters. I'm converting into meters. Minus 2 times the flange, which is point 00. I gotta go 0085. And the thickness of the web, 00584. And I got, I'll put it down here. I got 15.47 megapascal, which is less than our allowable. All right, that was 60 megapascal was the allowable. So we're nowhere close. This thing is 1/4 basically of what our allowable is. So we're good. So that means we use the W360 by 33. That's our best view. The process is the same every time. Yeah, it may be English units when we have different, loadings and different, different loaded beam. But the process is the same every time. And this is real engineering work. There's engineers out there right now somewhere doing this exact same thing we're doing. That's how they decide what size beams they put in this building that I'm sitting in right now. Some engineer went through and did this exact same thing, and that's how they chose the beam size. Any question about that? About this? No questions? All right. Well, sorry, we went a couple minutes over, but I wanted to finish that last little part and get that done. So I'm gonna stop recording. I'll tell you tomorrow we're gonna talk about something different. If you're tired of beams, we're gonna talk about pressure vessels tomorrow, and then we're gonna come back to beams again. So if you are hoping to never see beams anymore, then sorry, but we're gonna see more beams. But I'm gonna stop recording, and as always, if you have a question, you're welcome to stick around, and I'll address those. I have a question. I think I have to look, but I can look just here. I think it's Thursday next week. Let me look. Yeah, next Thursday, the 30th, is the last day of class. And then Friday is reading day. And the exams, I think, are Monday and Tuesday, but ours is on Tuesday. That following Tuesday at 4. So, any other questions before I stop recording?
Is that going to be a 3-hour exam?
No, in fact, I think, if I remember right, I think it says on the syllabus it's going to be an hour and a half.
Okay, nice. Thank you.
You're welcome.